Hello, everybody. Thanks, Playable, for the introduction. So welcome to today's webinar about the news on Gurobi 9.1. So I'll start with a 20-minute, 25-minute presentation about the general overview of what's new in Gurobi 9.1. Then we have Gu, who is presenting some performance numbers. And then I will take a specific look into the advances of the non-convex MIQCP part, and then Ed will take over and tell you something about the IIS finder and the news there. Okay, so let's start with the general overview. So here's the summary of all the news that's in Gurobi 9.1, at least the major ones. So of course, as always, we have been working on performance improvements. So we do have a number of performance improvements also in this release, but as I have just said, you will see those in more detail in Gu's talk, which comes after mine. And then one particular component that we added for performance of non-convex MIQCPs is the PSD cuts. So there's a new type of cut in planes for the non-convex MIQCPs. We will have that detailed in the talk that I gave after Gu's talk on granular performance. Then we have a new parameter called the integrality focus parameter. This is a new thing that helps you to avoid numerical issues with trickle flows. We have added some new heuristics that help you to find solutions faster and also to find solutions on models where the LP relaxation is really hard to solve. We've added some capabilities that you can now enter your user cuts already in advance to the model instead of having to use a callback. There are some additional things for multi-objective and the IIS, which Ed will cover in more detail. And then some Python enhancements, some enhancements to the compute server communication protocol. The record and replay feature has been extended to compute server and cloud. And we had some small additions to the tuning tool, and then some minor adjustments, which I won't cover here. Okay, so let's start with this integrality focus parameter. So many of you probably know that models that contain such indicator constraints here can sometimes show certain strange, numerically strange issues in the solution. So, and where does it come from? So let's first talk about what this is about. So an indicator constraint you would typically use for if you have a binary variable that controls some usually continuous or general integer variable. So for example, you have the decision whether you want to build a factory or not. And only if you decide to build a factory, only then you can produce something there. And the amount of things that you can produce is this, in this case, this X variable, and the decision whether you want to build a factory or not is this Z variable. And the indicator constraint, of course, says that if the Z variable is 0, so you don't build a factory, then the X variable needs to be 0 as well, because then you cannot produce anything. And then you can model this in different ways. So the first one is really the indicator constraint. So Gurobi supports that adding this indicator constraint directly internally during pre-solve. This gets then translated into an SOS constraint, which is here the following. So in order to model this particular indicator constraint, you have to introduce the complement of the Z variable. So the Z prime, you have to add this additional linear constraint that says that Z prime is equals to 1 minus Z. And then you just say that Z prime and X form an SOS1 condition, which means that if Z is 0, then Z prime is 1. And because Z prime is 1, the SOS says that X must be 0. Okay, now it could be that Gurobi automatically translates that SOS1 constraint into a big M constraint. This depends on the parameter, the pre-SOS1 big M parameter, and this depends on what is the value of the upper bound of the X. So if it's small enough, then we would translate that into this linear constraint that X is smaller or equal to big M times Z, and big M is now here the upper bound of X. Of course, you as a modeler can do this already yourself and just give us the model in this linear form. And then you have to consider these trade-offs between precision and performance. So using the SOS constraint, has the advantage that this won't have these trickle flow issues, which we'll see with the linear constraint. But because this SOS constraint is not part of the LP relaxation, it typically has an inferior performance. On the other hand, if you use the big M constraint as a linear constraint, then you have the improved performance because that is now covered in the LP relaxation, but you get this trickle flow. In particular, you have here this thing here that the Z variable is not identical to 0, but it's very small, 10 to the minus 5, say this is below the default integer feasibility tolerance, then the X variable can be as large as 10 to the minus 5 times the big M. And if the big M is very large, that could be a significant amount of flow or production that you are doing even though you did not build the pipeline or you did not build the factory. And that's the problem. So now what can you do about that? So in our new 9.1 release, we have included a new parameter that is called the integrality focus. If you set that to 1, then we try to avoid this trickle flow issue. So what we do is, whenever we see a solution that comes in where the integer variables are not exactly integral, then we would round the integers to exact integral numbers. And then with this modified solution, we would check again the feasibility of the linear constraints. And if that is not feasible, then we would reject the solution and continue branching on such an integer variable. And then the domain propagation, so the node pre-solve and the child nodes, may resolve this trickle flow, may or may not. We will see that this in the following example. So let's see, we have this linear constraint here where we have actually two big M conditions. So two binary variables, C1 and C2, and the X variable can only be non-negative if at least one of the two is 1. So in this particular example, it could be that you get an LP solution that has Z1 equals to 10 to the minus 6, Z2 equals to 10 to the minus 5. This is considered to be integral, but the flow variable, the X, is 1,100. So that is feasible for the linear constraint. So if you don't set the integrality focus parameter, then this would be a perfectly valid integral solution. But if you do set the integrality focus parameter, then we would round the Z variables to 0, and then see that now the constraint is violated by 1,100, which is, of course, far more than the feasibility tolerance of 10 to the minus 6. So, and what can we do about it? Now we would branch on the Z1 variable. So branch it down to 0. So now the LP solution does not necessarily need to change, because even this solution 10 to the minus 6 is still LP feasible. It's still in the feasibility tolerance. So the simplex algorithm does not need to do anything. So the old solution is still a valid feasible LP solution. And we check again. Of course, we have still the same problem of the violation of 1,100 after rounding the variables down to 0. But now we continue by branching on the Z2 variable. And now both variables are fixed to 0, both binary variables. And now domain propagation kicks in, because it now can conclude that the X variable needs to be smaller or equal to 0 as well. And now the solution does change, and also in the simplex algorithm. And one potential solution could be that the X star is now equal to 0, and the Z variables are now both 10 to the minus 6, say. This is still in feasibility tolerances. And now we accept the solution. And that is now a valid solution, and which does no longer have these trickle flow issues. If we apply that on our whole big test set on about 4,000 MIP models, what we can see is that in default settings, about 255 models behave different than when you set the integrality focus parameter to 1. So, and on those 255 models, you see here that 5 models in default settings come up with a solution that has really large trickle flow. So where after rounding, the violation is more than 10 of at least one linear constraint. And there are additional 15 problems where the violation is more than 1, and so on. You see that in the table. If you set the integrality focus parameter to 1, then most of this goes away. So you see here that the worst cases are now in the order of 10 to the minus 3 violations. So that is pretty much a very nice solution to that problem. But you pay a price because it makes the solves a little slower. So on those 255 models, the overrun time becomes 20% slower, and over the whole test set of 4,000 models, you pay a price of about 2% in performance by activating that feature. So this is why this is not a default setting. So the user needs to activate it explicitly. And it behaves somewhat similar to the numeric focus parameter. So if you set the numeric focus parameter, then it may also hurt performance, may or may not. And it may also help with numerics, but it is not guaranteed to do so. So this is the same for the integrality focus parameter. So you see here in these results, again, that there are also, again, 2 models with this 10 to the minus 3 violation. So it is not a guarantee that this will resolve all of the trickle flow issues, but it will resolve many of them. Okay, so let's look at the new heuristics that we added. So, and the most important one is this, what we call the no-rel heuristic. So this is about helping you to be able to find feasible solutions, even if already solving the LP relaxation is way too hard. Okay, so let's see. So the LP is now very big, assume in your model, and it takes much too long to solve, but usually our heuristics can only start with a LP solution, because that is where we are looking for feasible integer solutions around the LP solution. So what can you do now? So this is very tough. The no-rel heuristic helps you here. So it tries to find feasible solutions without solving the full big LP solution. And there is a secondary target. It can also help you to, if you have a limited amount of time and you want to find the best, as good solution as possible within this given time limit, then sometimes the no-rel heuristic can also be your friend. The downside, of course, is that it does not do anything about the dual bound. So you won't get any reasonable objective bound, and you won't get any reasonable assessment of your solution quality if you're using the no-rel heuristic for the whole part of your time. So of course you can do it a little bit and then go into regular branch and cut. That's also an option. So the no-rel heuristic is called between pre-solve and the initial root LP. Of course, you don't want to solve the initial root LP because it's too expensive. And what it does, it starts from some feasible or infeasible vector, which is constructed by some quick heuristic, and then it solves a series of smaller submaps in order to try to decrease the infeasibility, or if you have already found a feasible solution, to improve the objective value. And it uses multiple threads to do so, so to solve multiple submaps in parallel. And then it applies various neighborhood strategies to form these submaps. And those strategies are selected adaptively, so looking at which is working better, and to spend more time on those that are more successful. And then it basically runs forever until the specified time limit or work limit is hit. And this is where the parameters come into play. So you can control this no-rel heuristic by these 2 parameters. So one is the no-rel your time parameter, which specifies the time in seconds that should be spent in this heuristic. This is, of course, non-deterministic. So the time at which it will stop will be non-deterministic. So everything that happens afterwards is then also a non-deterministic thing, because it's based on wall clock time. If you want to have a deterministic version of that, then you can set the work limit. This is roughly similar to time, but of course, it very much depends also on your hardware that you are running on, how much time is actually, how the ratio between time and work is defined. Okay, that's the no-rel heuristic. Then let's look at the new feature of the pre-specified user cuts. So in Gurobi 9.0, if you want to add user cuts, then you can only do that through a callback. With Gurobi 9.1, we added the feature that you can also pre-specify those user cuts in advance by explicitly adding them already to the initial model. and you just add them as regular constraints, linear constraints, and then similar to the lazy constraints, you would set the lazy attribute, but in this case, you would set the lazy attribute to -1, and that would say this particular constraint is actually a user cut. But please recall the properties of user cuts. So a user cut has to be redundant with respect to the other constraints and the integrality conditions. So that means if you would discard a user cut, then the set of feasible solutions has to stay identical. Otherwise, this is not a user cut, if it would cut off otherwise integral feasible solutions. Okay, and then such user cuts will just be considered to be added to the LP relaxation as usual if they cut off the current LP solution. So we would apply the very same filtering mechanisms as for Gurobi's internal cuts. So IIS, we hear more about the IIS finder later from Ed. I just want to point out one particular thing that has been added. So IIS means the irreducible inconsistent subset. This is what you apply if you have an infeasible problem and you want to find out why it is infeasible, and then the IIS finder can help you by providing a smaller model, a subset of your model that is still infeasible. But this is a very complex algorithm in terms of running time, so it's much harder than solving your original problem. And what we added now is, while you are waiting for it to finish, you can see this output here, and we added this additional column, guess, that tells you what we think is a good guess about the size of the final IIS in number of constraints and number of bounds. But the more important thing that we added to the IIS algorithm is that we improved the performance quite significantly. You will see this in later presentations. So then the Python API. So that is our most popular API. So we are working hard all the time to improve it. And we did so as well in Gurobi 9.1. So in Gurobi 9.0, we already started to support sparse and then SciPy and NumPy matrices. So you can use those directly to feed it into constraints. And now we have extended that a little bit to make it more user-friendly by introducing the so-called mConstr class for matrix constraints. So this is a single object to model an array-like set of linear constraints. So as an example, you see here, if you call the addConstr method with a times x equals b, that is, of course, returns you a set of linear constraints. So in the previous version 9.0, this would actually return you a list of individual linear constraints. So this has changed, which means that if you were using that, you also have to change your code, because now this does no longer return a Python list of Gurobi constraints. It returns a Gurobi mConstr class object, which captures this set of constraints in a matrix-like way. And then you can use that mConstr object to query, for example, some attributes, and this will, of course, then return your NumPy vectors or vectors. So, and you could, for example, assign the right-hand side vector with this NumPy vector of all ones, or you can query the dual solution vector by stating this mc.py. This will then query, of course, all of the individual duals for the constraints and then give you that in a single vector. And it also enables you to express expressions in a concise, natural way. Another enhancements that you did to the Python APIs is that you are now able to install our Gurobi Python API through pip install. So use this particular command here, pip install -i, and then our server, GurobiPy. At a later point in time, we will hopefully be able to remove the necessity for this -i argument and have it also be supported on the public PyPI server. This is a package hosted currently at Gurobi, as I said, will be available on pypy.org sometime later. The installation is self-contained, so you don't need to do anything. You just do it and you have a running version. but it only comes with a limited size trial license. So it runs out of the box, but only for models that have at most 2,000 variables and 2,000 linear constraints. It supports these Python versions, so 2.7 and 3.6 through 3.9 right at the moment. Okay, and then let me talk about this record replay feature that we extended to work with the compute server and the cloud. So record replay is a very nice feature for debugging, in particular when you are going to contact our support. So you have a problem with your application, it does something strange, but in order to reproduce it, it doesn't suffice to write out the MPS file and send that to support. You really need to have your application somehow, but you can, of course, often not share all your application with the Gurobi support. So what you can do is you can activate the record parameter and let it record all of the interactions of your application with the Gurobi engine. And then you send this recording file to Gurobi support, which can then be used to replay it. Or you can also replay it yourself if you want it. This is very convenient. And now this is also possible if you have an application that uses compute server or the cloud. Just one thing that you have to be aware of. So we are trying to respect your privacy. So by doing this recording file, we will not store certain string parameters in the recording files, in particular your user credentials and the secrets that you need to set in order to connect to your compute server to the cloud. This is not stored in the recording file. Also file names like log file names and node file directories, this is not stored because we think we don't need to know how your operating system uses, which paths you have in your file system. And also your compute server URL is not stored. So we only store the stuff that are relevant for the recording. But of course, then if you replay it, you have to set such things explicitly through operating system environment parameters. Okay, and that's where I'd like to end this overview of the Gurobi 9.1 release. And I'm happy to take any questions that you have.
Let's see. Somebody asked about, is there any plan to create an API for Julia?
Yeah, that's a good question. So we are looking at Julia for already quite some time, and that always comes up in our discussions of what we want to do next, but it never, until now at least, it never hit the point where we really said, okay, we want to do it. So as you probably know, there is a Gurobi Julia connector not supported and done by us, but by the academic community that you can use Julia and Jump together with Gurobi. But for now, we don't have any plans to support that officially, so to create our own Julia API. But it's, of course, we may change our minds later when we think that Julia had gotten enough traction for us to become interesting for us.
Another similar question about features. So does Gurobi have an option to run Bender's algorithm as Cplex does? The short answer is no, not directly, but you can do it through the APIs. But do you want to elaborate on where that sits along the lines of a Julia option?
Yeah, so Bender's, no, so we don't have native support for Bender's decomposition. This is also something that we, of course, consider for future extensions. Currently, you would have to do that yourself, which means you create the master problem as a Gurobi model and you solve it, and then you have your lazy constraint callback, which would then solve the subproblems potentially in parallel. So this you would have to do that yourself, and then create the corresponding Bender's cuts as lazy constraints. So that's the only way you can do that at the moment in Gurobi.
Okay. Just a quick note that the guy who asked about pip has already tried the installation and is very happy that it works just fine. Another question, what about any support for R?
For R, so R is supported. So we do have an R connector in Gurobi, so you can use Gurobi through R. It does not necessarily support all of the features, but I think the largest parts of them.
Okay. Were there improvements to the numeric stability of non-convex MIQCP problems? I don't know. Maybe we want to defer that to the presentation 30 minutes from now.
Yeah, so I can just say very generally, yes, we have worked on that, but so we worked on performance quite a bit, and on the way we also discovered several numerical issues that we have fixed, but I don't have any particular details right now in my mind. I just remember that there were some.
Okay. Is there any way for user or developer to provide neighborhoods that can be searched with the no-rel heuristic? I believe the answer is no, but...
Oh, that's actually a good question. So the answer right now is no. So you can use the so-called partition attribute to specify partitions of your variables. For example, if you have a network that is defined over time, then you can partition the time steps. So which variable belongs to which time step, or which variable belongs to which region in your network, or something like that. But that is right now not exploited by the no-rel heuristic. It is only exploited by other heuristics that come later into play. But that's actually a good point. We could add that also to the no-rel heuristic.
Okay, and a sort of related question. I'm not sure how much you want to go into this, but could you please outline how submaps are constructed for the no-rel heuristic?
Oh yeah, so this is very similar to what we do in our other submap heuristics. So for example, RINs. So there is one of the strategies that no-rel considers is kind of a RINs strategy. Another one is more randomized, right? And so like trying to get to make as many rows as possible redundant without fixing too many variables and stuff like that. So there are three or four different strategies here, and then we have this adaptive control, this dynamic control that checks which strategy was successful in the past, and then it would put more effort on the ones that are more successful.
Okay, and so we're at 8:31. There are sort of a few other questions. I think I'll try to answer a few of them offline, and maybe we should go to Gu, and maybe also you can look at the Q&A yourself, Toby, and answer some of them in the chat and Q&A.
Yes, okay, so then I'll hand over to Gu for the next presentation on the performance improvements.
So I'm Zonghao Gu. Welcome to my session about Gurobi 9.1 performance. This is performance release. We made a lot of effort to improve the performance. We got nice improvement for all type of problems we support. For those items with red, I will give you more details. So first is about LP improvement. You know, Danzig invented simplex algorithm 60 years ago, and Kamaka invented interior point method or Berry method 30 years ago, and a lot of people made the effort, and now getting tougher and tougher to speed up. I mean, still we got some very nice improvement, especially dual simplex. The overall speed up is 29%. For harder model, it's 66%. For primal and barrier, we got 15% speed up, or a little bit more than 15%. For harder model, more than 30% faster. And the MIP improvement, especially MILP, is the most important. And a lot of people made effort to improvement the MIP. And getting, probably is toughest to improve now. And still we got some nice improvement. And the overall performance gain is 5%. And for hard model, it's 10%. And for MIQP, convex case, you have linear constraints and quadratic objective. We got 60% faster overall, and for hard model, 20% faster. And for MIQCP, you have quadratic constraints, also linear constraints, and you may have also quadratic objective. For convex case, the speed up is 13% faster overall, and for hard model, it's 57%. And for bilinear or non-convex MIQCP, we released this feature in 9.0, and this release we were able to, made very big improvement. And in next session, my colleague Tobias will cover it. And we also, made nice improvement on IRS detection. Quite a nice, big improvement. And we have another session at the end, and my colleague Ed Klotz will cover it. First, talk about LP performance. And I like to talk about the LP improvement for both barrier and simplex first. And when it's about pre-solve, we improve the one pre-solve reduction and get a little bit improvement, a few percent gain. And we also improve the dependent low reduction. What does that mean? For equality, linear constraints, you can detect whether they are linear dependent. If linear dependent, you can remove some linear equality constraints. And also, we have better decision to solve dual formulation. We use machine learning to decide. And also we use machine learning to decide which method to use, whether to solve it with primal or with dual. Also, we improved weak symmetry for LP, and those items with red, I just repeat, I will give more details. So now let's talk about LP improvement for simplex. Pricing is always important. So this time we worked on the dual pricing strategy. What means pricing? And then how to select a variable. Leaving basis or entering basis, there are different way, and one is DevX, one is steepest norm. Those mainly scale the violation, okay? And also how to switch between these methods. And we got quite nice improvement and on this work. And also we worked on scaling. And then one thing particular is about objective scaling. We often get the model, some model with very big objective coefficient, some very small. We worked on that, got a few percent gain. And you also know for simplex, it may cycle. So the technique to avoid cycling is perturbation. When to perturb, how much to perturb is usually an art. And then we worked on that, and we got a few percent gain. We spent quite a lot of time on LU factorization. You know the basis. If you want to have solving to get X solution or reduce the cost, you need to solve. And you first do LU factorization on basis. What you usually do, you first remove singleton columns, singleton rows, and now then you have a remaining matrix we call kernel. And now we also detect singleton 2x2 block and remove those. And we got some improvement on that. And for the remaining corner, what you usually do is we call Markowitz or Gauss elimination. And start it is usually sparse, and then you do few pivoting and it getting denser. And at the end it could be very dense. And usually the tough part to handle is it's not so sparse, not so dense. Then we improved that part and got some performance gain. And the other thing is how to select the element to pivot. Then, I mean, you can spend more time, you get very nice element. I mean, the fill-in is really small, but the cost probably big. If you can do very quickly, then you maybe the pivot element is not so great. So you just balance it better. So that's what we did. Now I like to talk about LP improvement for barrier crossover. One is, I mean, improve the ratio test for primal push. What means primal push? So you get a barrier solution, you have some primal super basic variables, not at the bound. And then you do ratio test whether push into basis or push into the bound. And the barrier solution usually not so nice and often will become infeasible. Then you want the ratio test, then we improved. And another thing is better handle the numerical issue, like initial cross basis. I mean, usually barrier solution is the initial crossover basis is usually numerical bad, and we improve that. And also for barrier parallel improvement, we discovered one part for barrier parallel. It's not so well done. So we improved that, and then you will see for machine with more than 4 physical cores, you see some nice improvement. So now let's talk about approach to solve due formulation. What's our approach? We first use original model to formulate the due. And then we apply the pre-solve on the due model, and then solve the pre-solved model. Alternative approach, apply pre-solve to the original model to get pre-solved model. And then you formulate the due model based on the pre-solved model. Then you solve the due of pre-solved model. So main difference is the order, whether you apply pre-solve first or apply formulate the due first. And each method has pro and con. I mean, the alternative is maybe better to estimate the size. So now we focus on our approach to better estimate the size to decide whether to solve the due formulation. So first is estimate the size of the due atom. So we exclude the rows and column in due formulation that will obviously be removed by pre-solve. The second thing is use machine learning. Now, machine learning is quite hard. The good thing about that is now the tools is now very, a lot of tools are available to use. So what we did is find important factor to decide whether to solve the due formulation. We fed the data to scikit-learn to identify key inputs. We feed like the number of columns, number of rows, number of free variables, number of bounded variable, etc. And we get only one important output is the aspect ratio. The columns divided by number of row, and this is similar to what we already do. So just verified. And then second, we're using also machine learning to decide which method to use, primal or simplex, to solve the due formulation. And we're using the similar input to fed it to scikit-learn, and machine learning give us a nice formula to decide. And I would say most expected, you look at the formula and understandable, not all. One part is not sure, but we take it. And we also did some manually adjust a little bit to improve. So we get nice improvement on some models. Now let's talk about weak symmetry for LP, as known as LP folding. So look at this example. You see there are 4 variables, 3 constraints. And if you compare variable Wx, their symmetry or coefficients are 3. But if you compare x, y, z, and 3, 3, 2, 4, but 2, 2, 4, 4, or maybe symmetric. But it's hard to believe x, y. I mean, coefficients are different. They are also symmetry, but so this is not really symmetry. We call weak symmetry. The only thing matters is sum of coefficients is equal to 9 for each column. Sum of coefficients for each row is equal to 12. So conditions for weak symmetry. So you first divide the rows and column into classes, and then the sum of the coefficients in a row is equal for each row in the same class, and the same for the each column class. And also objective coefficients and the bounds are the same for the variables in the same class. And the right-hand side and the sense are the same for the rows in the same class. So now let's talk about the property of LP weak symmetry. Given a solution X star, and then you just look at the solution in the same class. And for those variables, you just take average value. Then you can create a new solution X prime. And you can easily to check X prime is also feasible solution with the same objective value. What does that mean? Then you can let all the variables in the same class equal. Take the average value, okay? And then all the rows in the same class will be identical. I mean, based on this observation, you know how to do the symmetry reduction. So you combine all the variables in a variable class together by adding the up coefficients in the rows. And then you just need to keep 1 row for each row class. So you can look at the references, some call symmetry LP symmetry, some call LP folding, and there are several reports with computational results. You know also many LP solvers have the feature. We have it since Gurobi 7.5, about 2.5 years ago. And the key part is to convert non-basic symmetry solution to a basic one. How? I mean, the improvement is first is detection. Now, as I mentioned the example, now we catch more general cases, and also we speed up handling how to find it by handle the sparsity better and the hashing better. The second is about the converting to the basic solution. For 9.0, for the previous release, what we do is we use super basic code to convert for simplex. So we only that code is only used for the corner case, not used much. I mean, rarely people will give us that super basic information to use to solve with simplex. Now for 9.1, the main change is using the crossover to convert non-basic solution to basic solution. Crossover is basically simplex. So it has initial cross basis construction. So you have a lot of super basic variable. After this one, you already pushed a lot of super basic variable into basis. So, I mean, then save a lot of pivoting. And that code also check many different numerical bad signs. Will restart if it's bad enough. And the code is heavily tested and refined. So for those model with a lot of symmetry, and 9.1 is quite better than 9.0 for the simplex. For barely, so what's the improvement? For the previous release, we do crossover just once. So what's the procedure? You first apply place-off, you get a place-off the model, then you apply symmetry. You further reduce the model. Usually further reduced model is quite small. So the previous version 9.0 were using barely to solve it, then immediately uncross that solution to the place-off the model, which is often quite bigger than the symmetry reduced model. And the uncrossed Berry solution is usually not clean. Berry solution is not clean, so uncrossed solution is not clean, then you use crossover from that unclean solution is usually numerical not stable. So this version, what we do is, because symmetry reduced model is small, and then we apply place-off crossover first and get a clean solution. And then we use this solution to uncross. Then we get a clean solution to the place-off model. That solution also has less super basic variable. So you save the iteration and also become numerically more stable. And we got a nice improvement, although not as big as for the simplex answers model with a lot of symmetry. Now I like to talk about MIP performance. Some are for MILP, some for MIQCP. And first, we improved simplex, and there are some carry over to MIP. Roughly only 2% gain from LP improvement. That's a little bit disappointing. And now let's talk about other things we did. First is heuristic. As already Toby said, we have new heuristics, nowhere heuristic. Also, we have some new variants of rings. And we also improved existing heuristic, for example, by adjusting some MIP heuristic setting or adjusting improvement heuristic. And in terms of performance, the heuristic work improved the performance by 1 to 2% overall for the optimality. You know, it's usually heuristic won't improve the performance for optimality that big, but it greatly improved the performance for finding better solutions. For applications, that's very important. So let's talk about the result for finding better solutions. The test set, we pick all MIPLIP 2017 open problems. There are 245 models. You can download all these models from zip. And runs, we set 1 hour limit with for 9.0 default, 9.1 default, 9.1 nowhere heuristic. The winning measure is a solution is at least 1% better in terms of objective value. All these runs will hit time limit because they are open models. Now, if one run doesn't find any solution, any feasible solution, then the other run finding a feasible solution will consider as a winner. So compare with 9.0 default with 9.1 default, there are 85 models with solution difference by more than 1%. So 9.0 wins 16, 9.1 wins 69. So quite a big difference. And if you compare with 9.1 default with 9.1 nowhere heuristic, there are 190 models with solution difference by more than 1%. 9.1 default win 29 models, and 9.1 nowhere heuristic win 90 models. Also quite big difference. Now we like to talk about opt approximation tangent cut for MIQCP. This is mainly for convex, but also apply for non-convex case. So for a convex MIQCP, for relaxation, you have choices. Solve LP relaxation or QCP relaxation. LP relaxation usually is quick to solve and you have warm start. QCP is stronger, but you don't have warm start. So if you solve LP relaxation, then you solve LP relaxation, get a solution, and then you check quadratic constraints. If it is violated, then you generate tangent cut. Then you add to LP relaxation. That approach we call odd approximation method. Before talking about tangent cut, I would like first talk about the forms of quadratic constraints. Standard form, second order comb, then you some sum x squared less or equal to y squared. Very simple, no cross product term. And the general form, you have cross product term. Sum qij times xi times xj, I may not equal to j. Then add linear term, sum aj times xj less or equal to b. So for input, it's easy choice. You just pick the general form, which covers the special form. I mean, standard form, second order comb. For internal, we have a parameter to control. MIQCP form. -1 is auto. 1 is if you have a cross product term, it won't translate, it will keep general form. If 1, it will translate into second order comb. And 2, it will first translate into second order comb. If second order comb could have like 10 variables, then you further disaggregate them into smaller comb, each comb with 2 variables. And I mean, the translation sometimes is quite expensive. You involve LL factorization and introduce new variables. Now let's talk about tangent cut for quadratic constraints. There are many options for cutting off LP relaxation solution X. I mean, you can solve QCP relaxation, and then you're using QCP relaxation solution to generate tangent cut to cut LP relaxation solution. But that's really expensive. If you don't solve QCP relaxation, then usually separation is very fast. So then you want to focus on the quality. Quality usually using maximum violation to measure. Okay, so we focus on maximum violation. Now first talk about a tangent cut for second order comb, standard form. So giving a relaxation solution, x star y star with sum of x squared greater than y squared, okay? This means violated, okay? And then this solution is violated, is violating the quadratic constraints. Then you can define y prime equal to square root of sum x squared. And then it's easy to see the new point x star y prime will satisfy quadratic constraints at equality. So it's on the SOC surface. So then you can use this point to compute the tangent plane. It's easy to show. It will cut off the solution, x star y star. And also you can show the distance to this solution is maximum among all the tangent plane cutting off the solution. That's easy case for standard form SOC. Now for the general form, that's not that easy. So first, how to find a point on the surface given a solution x star is violating the quadratic constraint. Violating means left-hand side for this x is greater than b. So it's not so easy to find a point on the surface with tangent plane will cut off x. I mean, I wouldn't say it's very hard. I just want first to give you an example. Here, if you look at example, very simple, x squared less or equal to y, not y squared, If y squared, then standard form, SOC. So now you have a point violate the quadratic constraint. So for this point, you can keep y unchanged. You just move x, then you can hit the surface, P1. You can generate a tangent plane to cut off this solution. Or you can keep x unchanged. You change y to hit surface and get P2 and generate a tangent plane. And which one is better? And now you can using the distance. This solution to T1, the distance is D1. And to T2 distance, you just project to T2 and then you can get the distance. And it looks like D1 is bigger than D2. So this is T1 is better. But if y value is negative, okay, here, then you keep y unchanged. You move x, you may not hit any point on the surface. So now I want to talk about how to find the cut with maximum distance. Our approach is iterative. So now given a violated point, I'm using the same example, okay, see. Then you have this point violating quadratic constraints. Then you have some way to find a point on the surface. Then you generate tangent cut. Will cut off the solution. For previous Gurobi versions, it will just add this guy into the LP relaxation. Now what we do, we want to improve this. We first project the point to the plane. This is line segment. We don't stop there. Extend it to the surface, okay? And then use this new point to generate a new tangent plane. And then you repeat this procedure, project to the plane and extend it to surface and until 2 points. One is on the surface, one is the point on the plane. It's the projected point. If 2 points are the same, you know you get maximum distance. But I mean, iterative approach or Newton approach won't be really same. You have some tolerance. If they are close enough, you stop. And let's say stopped at PM, then you generate the tangent cut. And then you add to the relaxation. So the performance impact of the improvement, you can see. For the internal convex MIQCP set, we get 3.3% speed up overall. And for harder model, 10% speed up. For internal non-convex MIQCP set, because for non-convex quadratic constraints, translation is different. It's less involved. I mean, the general form of the quadratic constraints, so you see less improvement, 1% overall. Now back to the performance summary. Now you can see this is for the simplex, the speed up, then barely MIP, and then convex cube, MIQP, MIQCP, and then non-convex MIQCP, then Toby will talk about that, and then IRS detection. Thank you. So I'm ready for the questions.
Okay, thanks, Gu. So we have quite a large number of questions, so we need to be a little bit quick to answer them. So first one is, why does pre-solving before formulating the dual speeds things up instead of dual formulation and then pre-solve?
It's just hard to say based on, I mean, which one is better. I think, I mean, maybe still first apply pre-solve is a little bit easy to estimate the size and decide. But just it's a little bit more involved. It's my experience is it's harder to predict. So then we picked our approach.
Okay, then we have a question, so it sounds like you fit a binary classification model to determine if it is better to solve a dual or primal formulation. Would you be willing to share what class of model was fit? For example, was it a decision tree, logistic regression, or some other classification model?
I think, Toby, that's maybe you did that. You maybe you
So
want to answer it.
It was a decision tree because we definitely wanted to have something that gives us an answer that is interpretable. So that's why I also played around with support vector machines, but this didn't really gave something that I could understand somehow, and I really wanted to understand what was going on. So decision tree was good here. So then next question. Would Gurobi have plans to support model serialization in the near future? So right now, MPS file would be the way to go.
What means model serialization?
Well, that you write everything into a file, or you can send it to something else, and then it would be identical if you read it back in the whole state. That's serialization, right?
Is that our record replay feature? No, the model is, I mean, for reproduce MPS file for the model, keep the 4 positions, so it's fine, but
yes. So the MPS file is right. So this captures everything of the model formulation.
Yeah.
Of course, you won't be able to save the current state. So, for example, if you have solved your MIP partially and then you have interrupted the solve, then there's no way of saving the search tree and then loading it and resuming it. So
that issue is really, it's not easy. If especially the concurrent or parallel deterministic parallel is really hard to have this. Yeah.
Okay, then I'd like to answer here the next question. So there, an issue with pip install that gives us, of course, only the restricted license. So this license is restricted by 2,000 columns and rows for linear models and smaller for quadratic models. But the user has a full license. So what can they do? So of course, yes, you can just put your full license into one of the default locations, or you can also set the operating system environment parameter to point to that license, and then we automatically use that full license, and you won't have any limits anymore.
Yeah.
Okay, then Gu, here's a question for you. So why did the significant improvement in dual simplex does not lead to a more substantial improvement in MIP performance?
Yeah, so let's just take the dual formulation. Solve the dual. This part only apply to root, that's right. Then for the nodes, it's really nothing to do with the dual formulation. Then then root is usually cheap. That's one reason. Another is if you about symmetry stuff, weak symmetry, is also about just the root and the nodes to solve, because you have the one start information. It's really hard to combine those. So that's not. Then the work on the LU factorization, usually, this is for very large model. For small model, the improvement is small. So that's somehow, it's disappointment, but if you think about, look at the improvement, then you see, you see the reason.
Okay. So here's one more question I want to ask very quickly. Do we have a standard way of giving to Gurobi a bilinear problem? So like LP or MPS file?
That's we extended it. You directly, we always treat as MIQCP, that's for bilinear, that's right. I think that's really no overhead. You just, X times Y less or equal to something, that's, you can treat it general form. We just recognize that. I don't see any issues there. Toby, do you see it?
No. It's correct. So you just specify it as regular quadratic constraint, and that of course you can put it in LP or MPS file, and that's it.
Yeah.
Okay, so let's stop there because we are already almost 10 minutes too late now. Maybe we have in the end some more time to answer the additional questions, or we can answer them during our additional presentations by answering them in text. So thanks again, Gu, for your presentation. So
I stopped sharing.
Now come to the third presentation, which is about the non-convex MIQCP. You should now be able to see my slide. So the advances in the non-convex MIQCP solver in Gurobi 9.1. So we started to support non-convex quadratic objectives and non-convex quadratic constraints with Gurobi 9.0. And since then, we have worked quite a lot to improve numerical stability and performance on those models. And here you see an overview of where all those performance improvements came from. And it is very similar to what we always see with MILP, namely that those performance improvements do not come from a small number of big changes. It's really a set of a large number of individual changes, each of them contributing with a few percent. So, one of the most important parts, which is also similar to MILP, is pre-solve. And all of what we did to pre-solve already improved the performance of the non-convex MIQCP solver by 33%. And most prominently, you see here that this one, that we are now adding quadratic equations to other quadratic constraints in order to cancel quadratic terms. So that's this one alone contributed with 18% to performance. And those that are marked here in red, this is what I will also cover in this presentation. And then in addition, what is not, of course, in MILP, what is very important for non-convex MIQCP and also for convex MIQCP is how you translate the general quadratic constraints into a form that the solver can deal with. And in this particular case of non-convex quadratic constraints, the form that the solver internally can deal with are bilinear constraints. So you need to introduce additional variables and split constraints into different individual terms and stuff like that. And how you do that, there are multiple ways. This significantly influences the performance of the solver, and we changed that a little bit. And this gave a 36% overall speed up on our test set. So that no pre-solve is also an important feature, not as important as the regular pre-solve. The changes that we did summed up to 4% improvement roughly. And then we have, of course, branching. We adjusted the balance of the two branching rules that we are using for non-convex quadratic constraints, one of which is based on the reduction in the volume of the McCormick polyhedra when you split it, the domain of a variable into two. And the other one is just based on the violation of the bilinear constraints in which the variables appear. And by adjusting the balance of these two rules, which is a very simple change in the code. So I just replaced a logarithm, so a square root by a logarithm, and that already gave a 15% performance improvement here. And then cutting planes is, of course, also very important for performance. So here in this release, we introduced a new type of cuts, the PSD cuts. So of course, this is not nothing that we invented ourselves. It's just standard literature. We just implemented it in Gurobi, and this gave 15%. And overall, all of the changes to cutting planes got us 22% improvement. And then there are a number of other things in heuristics and in the simplex integration. And of course, all of the changes that we did to improve MILP and linear programming and quadratic programming, they also have an effect to non-convex MIQCP. And from those changes, we got another 50% roughly of performance improvement. And that adds up to a more than 4x performance improvement on our test set for non-convex MIQCPs. So that's really a big improvement. Okay, let's talk about some of those in particular. So pre-solve. So as I said, adding quadratic constraints to other quadratic constraints can be used to cancel non-zeros, and that is very useful. So if you have a quadratic equation, you can just add them to other quadratic constraints. But then as another case, what you can also just look at is parallel quadratic constraints. So, and here you see an example of two quadratic constraints that are parallel. So of course you see here that the one is just the other one multiplied by -1. So that is actually an implied equation. So they can be merged into an equation. Another case is that one of the two constraints would be dominated by the other, and then you can just discard the identical or dominated one. This I have seen actually happens very frequently in the submaps that we solve by primal heuristics, not so much in the original problems in our test set. But it's very, very easy to detect those in terms of performance and running time. So the algorithm is very similar to the linear case that we already had, which is about hash functions and sorting and scaling and stuff like that. And we just do the same, so we only need to extend it by also putting this quadratic part of the constraint into the hash function, and that's basically it. It runs very, very fast in practice. Okay, so just doing that, just parallel quadratic constraint detection and removal of redundant constraints here affects about 20% of the models in our test set. It gave an 11% speed up on those models, and overall, if you also include the other 80% of the models, that's an about 4% speed up. And what we do when we add such changes to our code, we always run the old version and the new version with 5 different random seeds, and then we look at the individual models, what has happened to them, and we consider a model to be a consistent win if the new version is at least 10% faster on that particular model in at least 4 of the 5 random seeds. And otherwise, if it was almost always slower, then it would be a consistent loss. And what you see here is that there is no model with a consistent loss. So this basically means that this pre-solve reduction does not hurt. And that's a very good thing. Okay, and now coming to the more powerful reduction, which is this cancellation of quadratic coefficients. So if you have these two constraints here, let's say in this one case, you have one equation and then an equality, or the second one could also be an equation, and they are identical in the quadratic part. They can be different in the linear part and in the right-hand sides. Then you can just subtract the first equation from the inequality, and that would cancel all of the quadratic constraints. And so the second one becomes a linear constraint. And that is very nice. And there is another case in which both of them are inequalities. Then it's more difficult. But what you can do is you can introduce an auxiliary variable s that basically captures the quadratic part here. And then you have this quadratic constraint here to define what s is, and then you replace the quadratic part by this variable s. So you have turned these two quadratic inequalities into linear inequalities, and you have added another quadratic inequality. So that's also nice. Doing that affects about more than a fourth of our models, and on those it gave almost 40% speed up and an 18% speed up overall. Again, we don't see here any consistent losses, but we do have a number of consistent wins. So this is also a very nice pre-solve reduction then. You can also think that you could do the same to the objective function. So adding quadratic equations to the objective function in order to delete non-zero quadratic elements of the objective function. And we do this, but unfortunately, it only affects 7 models of our whole test set, which is less than 2%. And on those, it gives a little bit of speed up, 5%, but of course, it's just 7 models. So overall, it's almost nothing. So cutting planes. So we added PSD cuts. So those are controlled now by the new PSD cuts parameter. So if they seem to hurt on your model, you can disable them. And they are based on the literature about those PSD cuts. Two sources you can find are from Fiorelli and Fraticelli from 2002, enhancing RT relaxations via a new class of semi-definite cuts. So this, and then there is a nice paper from Qualitza, Bellotti, and Margot from 2012. They have actually implemented all this into the COIN-OR framework. So linear programming relaxations of quadratically constrained quadratic programs. And basically what we do is pretty much the same. You have, after you have translated all your non-convex quadratic constraints into bilinear constraints, so this is what we are dealing with. These bilinear constraints, we have these Yij variables that should be equal to the product of xi times xj. And if you write that as a matrix equation, so suppose you have all of the Yij variables in your model, which is actually not the case in practice, but we come to that later. So suppose for now we have them. Then you have this big capital Y matrix, which has these Yij as their components. And this is equal to the variable vector x times the variable vector x transpose. That is what the set of equations here is saying in matrix form. And then you can relax that matrix equation by using this larger equal sense here in the PSD sense, right? So that means if you subtract if you move the XX transpose to the left-hand side, it just means that this matrix Y minus XX transpose should be positive semi-definite. So that is a relaxation of this equation. And then that is actually the Schur complement of a PSD inequality over a matrix that is has one additional column and one additional row. The row is here in the top left corner, you have a 1, and then the row in the first row would be the X transpose vector, and the first column would be the X variable vector, and then the rest of the matrix would be the Y. And so this here is equivalent to saying that this matrix is positive semi-definite. Okay, now we separate cutting planes. Namely, positive semi-definiteness just means that for every vector V in this Rn plus 1 space, it is true that V transpose times this matrix times V is non-negative. And that also means that if we are able to find such a V where this is not true, then this is a valid constraint that cuts off the current LP solution. So that's a cutting plane then. So what are we going to do? Well, of course, we try to find negative eigenvalues for that matrix, because then the corresponding negative eigenvector would be a vector V that has this property that this is negative. Okay, so, and in practice, what we do is we separate such PSD cuts for up to 10 product variables, which means that this matrix for which we need to find negative eigenvalues has a size of at most 11 by 11, right? Because it has this additional first row and first column. We only do this if we find sets where all of these Yij variables actually exist. So they do not need to exist in the model. We only create them if we have such bilinear products xi times xj. And so what we are looking for is we are finding cliques in the graph that is defined by the nodes of the xj variables and where the edges are these Yij variables that exist. So if we find a clique in that graph, then we have such a set of up to 10 product variables Yij where we would look into this matrix and try to find negative eigenvalues. So now we form this matrix. Now here is the LP solution values that you have for the current LP relaxation solution. And we find negative eigenvalue for that matrix. And then we calculate the corresponding eigenvector, and that gives us our cut, which is, if you multiply it out, this thing here. Okay, and if you do that, this affects about a third of all of our models, and it gives a 32% speed up on those models, and overall a 15% speed up. So now we are seeing some models with consistent losses, so which is not surprising for cutting planes. This happens all over the time. For cutting planes that even though you add some cuts and this nicely improves your dual bound, it can still be that overall the performance is degrading. But it happens only for 5 of the models, while it consistently wins on 28 of the models. So overall, it's a win, but it could be that for some problem classes, you want to disable those pins. So, and if you compare these PSD cuts to the other cutting planes that we have added specifically for non-convex MIQCPs, then you see this picture here. So if you run Gurobi 9.1 in default settings and then normalize by that runtime, then of course the default settings give you a value of 1.0 in the geometric mean of the running times. Now, if you use the default settings but disable the RLT cuts, which we have already added for version 9.0, then you lose 65% of performance. So that means the code on average runs 65% slower than in default settings. So RLT cuts are very, very important for non-convex MIQCPs. If you do the same and disable BQP cuts, then there's almost no difference. So these cuts aren't that strong, just 1% difference. My sense is that they are mostly already covered by RLT cuts. But the PSD cuts are actually new. So they bring something new to the table. They really give a 15% performance improvement. So in other words, if you disable them, but leave RLT and BQP cuts enabled, you still lose 15% of performance. Okay, another improvement that we did is that we are now able to use to find implied equations for quadratic constraints, and that is important in particular for cutting planes. So recall the PSD cuts again. So we formulated them with these YIJ variables here. But so what you get here is you get this quadratic constraint actually, and now we need to get you get this linear constraint, but actually what you can view it is you can just formulate it in the x variables, and then it would be a quadratic constraint, and then only in the second step you replace the square terms and the mixed quadratic terms by the corresponding Yij variable. Now the question is, that works of course if you have bilinear equations, so if that Yij is equal to xi times xj. But can you do the same if you only know bilinear inequalities? So if you have only Yij smaller or equal to xi times xj, or Yij larger or equal to xi times xj. And of course, the answer is yes, you can do it if the sign of the corresponding coefficient is correct. Right? So, and the very same question is for RLT cuts and PSD cuts. So that means in more general sense, you are given a quadratic constraint, in this case, a quadratic cutting plane, and such relations for the Yij and the xi times xj products, which could be equations or inequalities. How can we derive a valid linear cut? And then you have to look at the sign of the coefficient, and the positive sign, you can only use this relation if it is an equation or a smaller equal inequality, and for a negative sign, you can only use that if it's an equation or a larger equal inequality. And that means, that shows that equations are nice here. So we want to try to show that certain of the inequalities that we know are actually implied equations, because then we can exploit them better in our cutting plane separation. So how can we do that? So let's take a look at pre-solve now. So given a quadratic constraint in its general form, an inequality, and it looks like that. And now we can split the linear part into two parts, and I do that for a certain reason. Namely, if we can now show that either of the two things here are true, namely that for any solution to the x prime variables and to the y variables, we can always change the x variables in such a way that this a times x scalar product increases up to the value of b in total. If we can always find such values x without degrading the objective value, and also not making other constraints infeasible, then this is an implied equation, right? Because we can always find such x if we can show that. And the same for the y's. If for any x prime and x, we can always find y's such that this becomes an equality. And of course, the other constraints stay feasible and the objective doesn't degrade, then this is actually an implied equation. And this we do in pre-solve, and that helps cutting planes. And it also helps pre-solve a little bit because it allows more substitutions of bilinear term square product variables. And it also helps a little bit in domain propagation, which is part of pre-solve and also of no pre-solve. It helps in the heuristics, and it also may help in branching. So doing that affects about a third again of our models, and it provides a 9% speed up on those models and a 4% speed up overall. So that's also a nice addition. So you see here that all this comes together. So all those smaller or larger improvements in that give this very large speed up. And this is what you see here in this ASCII-based table. This is stuff that we are looking at all the time. This is the output of our performance comparison tools for 2 runs. And this is the comparison of Gurobi 9.0 versus Gurobi 9.1. And you see here that if you look at the time ratios and the bracket of models that solve in at least 1 second, so that means it excludes all the trivial ones that are very fast for both of the versions, then you see here this ratio, and that means this is more than a 4x speed up for Gurobi 9.1. And if you look at the even more challenging models where both of the solvers need at least 100 seconds, where the slower of the 2 solvers needs at least 100 seconds, then we get more than a 9x speed up on this test set. And you also see here that the number of models that we are not able to solve within the time limit drops dramatically. So 31 models can be solved with Gurobi 9.1, but not with Gurobi 9.0. And there are only 4 models that can be solved with Gurobi 9.0, but not with Gurobi 9.1. And here is finally a comparison of public models that has not been run by us, but by Professor Hans Middelmann from Arizona State University. And you can find those on his public benchmark set website here. So he had done this already for Gurobi version 9.0, and now he did this also for Gurobi version 9.1. And if we can compare to other solvers that are able to solve such non-convex MIQCPs. He is doing that on the public QP-lib test set. He splits this into 5 different categories. So 3 of them are not interesting for that particular comparison because this one, all the variables are binary, then the whole thing just translates into an MILP. So this is really then just capturing MILP performance and not non-convex MIQCP performance. If everything is convex continuous, then this is actually a second order cone programming. So this just evaluates performance of the barrier solver. And if it's convex discrete QP, then it's just a convex MIQCP. But we want to look at non-convex, and this is these 2 sets here, continuous non-convex and discrete non-convex. And on these 2 test sets, so Gurobi 9.0 was already 1.59 times faster than the second fastest code, which in this case is Antigone. But Gurobi 9.1 is now almost 4.7 times faster than Antigone, and it can also solve a larger number of models of this test set of 57 models. And even more extreme is on discrete non-convex, where also the Gurobi's ability to deal with integer variables comes into play quite a bit. Here, the second best solver is FiberSkip, but Gurobi 9.0 was already much faster, and now Gurobi 9.1 is more than 10 times faster than the second best solver on this relatively small test set. And this is where I'd like to stop this presentation, and I'm taking some more questions. Thanks.
So, Toby, I saw some new question we answered by typing some answers, and I now see only 2 new questions. One is about the canceling. You add quadratic constraints to cancel other, and then it may be close to 0. And is there a parameter to control that? I think that's
Yeah, so there is no parameter. We use just an internal threshold, which would be 10 to the minus 13 in this case. So this is what we then consider 0. If it's larger, then we would still keep the coefficient.
Okay. The second is may not related to your talk session, and the question is, what are the 3 most effective place-off techniques used by Gurobi in supply chain problems?
Ooh, in supply chain problems.
Should I answer or you?
Yeah, so I think, so overall, one of the most important one is the aggregator.
Yeah.
And then the clique merging is also very important, but I don't know if that applies so much to supply chain. So maybe you have more experience.
Yeah, I think we have some bigger guys. I mean, SAP, Oracle, or some others using our Gurobi, and based on my past experience, I mean, some just using LP. I mean, now a lot of using MIP. Usually for supply chain, the place of the model is quite smaller than compared with the original. And I think there are a lot of redundant constraints. Just some simple place of reduction can get rid of a lot. And aggregation, certainly one of the important is if, I mean, like network type of constraints are often. But I wouldn't say how to name the 3 most effective. But first is, I mean, place off reduce a lot, and aggregation may be important, and also a lot of redundant ones.
Mm-hmm.
Yeah.
Okay, so then I think we move on to
Yeah.
the last talk given by Ed. So Ed, the stage is yours.
So this is about new features in the Gurobi Infeasibility Finder, and we're going to start by describing the problem that the Infeasibility Finder needs to solve or compute, and then we'll look at some of the basic operations it has at its disposal. We'll consider Gurobi 9.1 performance and improvements, and then we'll finish with a couple of examples. Excuse me. So the problem of interest is, given an infeasible system of constraints, which typically will be the whole model, we find a single irreducible inconsistent subsystem, or IIS. So it is a subset of constraints that is infeasible, but also minimal in the sense that removing any constraint renders this subsystem feasible. So there's no excess baggage or superfluous constraints included. And by constraints, we mean not only linear or nonlinear constraints, but bound constraints as well. The purpose of this is primarily to help the modelers figure out the source of the infeasibility in the model. So smaller size is better. And we will focus on the computational challenges for infeasible MIPs, because this is really pretty easy to solve in the LP case. And here is a nice way to visualize the IIS computations. So we use this node and oval depiction here, where each node or dot corresponds to a constraint, and then the ovals correspond to these IISs, or minimal subsets. So what we see here is we have 3 IISs. Each oval identifies some constraints in the IIS. Some constraints can appear in multiple IISs. And then also, they're all minimal, but only one is the smallest one, namely this one in the dashed oval at the bottom right of the slide. So we'll use this to sort of figure out how things work when we do these computations. And as in the previous picture, it is not uncommon that a model will have multiple IISs. And let's start simple. Here we have three constraints where we set the same variable to three distinct values. And that creates three distinct IISs, namely every pair of constraints is infeasible in a minimal sense, where you can remove one constraint and the pair of constraints are no longer infeasible. Now, this seems really simple, but it actually will come back to annoy us later on as sort of a counterexample that illustrates some performance challenges. So our computational approach is to maintain two sets. So we do both a build down and a build up approach. So the build down approach involves viewing all the eligible constraints as candidates for the IIS, and then we're going to try to systematically remove constraints to reduce the size of this infeasible constraint set, which we'll call C for candidate set. Excuse me. And then we have a set K of known IIS members that starts out empty, but we try to build it up. And then as we continue to iterate, these sets move towards each other in size, and we can stop when they are equal to each other. Let's now talk about some of the basic operations that we have at our disposal. We can delete constraints one at a time. We can delete constraints in groups. We can delete single constraints in parallel, or we can try to add constraints to discover a smaller set of constraints that are infeasible. Now, in the LP case, we can sort of dispense with these relatively simple operations because we can use basically the dual variables associated with a primal feasible or dual unbounded model to essentially get the IIS in a single step. Let's now look at single constraint deletion. So we start with a single constraint. So we'll just pick one arbitrarily, this red one that is sort of highlighted with the star. Let's remove it and solve the remaining subsystem. There are three possible outcomes. The first outcome is that we're still infeasible. Well, that's fine. Then this constraint is irrelevant to the IIS computation. We filter it out, and then we move on recursively to the next iteration and can go on with filtering by single constraint deletion. The second case is that removal of one constraint makes the whole set of candidates feasible. In this case, we know that the constraint belongs to every single IIS in C. Now, since this example here doesn't really illustrate that, we'll come back to that on the next slide. And then the third example, because we are solving subMIPS, is that we decide to put a time limit on our MIPS, and the MIP hits the time limit without any conclusion. So in this case, we don't really have a useful conclusion, but what we can do is we can defer this constraint and come back to it later when we've got additional reductions in the candidate set. And by then, hopefully, the subMIP will be easier to solve. Now, let's go back to this condition where we're feasible, and let's illustrate with this picture here. So here we first remove constraint C1. So that gets rid of the small IIS. That makes that, because this set of two constraints is minimal, removing one constraint gets rid of the infeasibility in this small IIS at the bottom right. And now we're still infeasible. So now we do a single deletion on constraint C2, and we suddenly become feasible. So what that says is C2 can now be added to this known set in the IIS, and then we can again proceed. What this also illustrates is that there's some real benefit to having the so-called IIS cover, namely a set of constraints whose removal gives you a feasible outcome immediately. But unfortunately, the IIS cover computation is significantly more expensive than computing a single IIS. So Gurobi and all the other MIP solvers do the latter approach instead. So what this means is we may need to correct the computed IIS and then compute another one. However, at the same time, in many cases, when you figure out what's going on in one of the IISs, that may shed light on the overall issue in your model that has created multiple IISs. So when you propagate your correction to the rest of the model, you may find that you actually just need to get the first IIS to figure everything out. And lastly, we've been talking about, constraint deletion in this algorithm, but when it comes time to correct the IIS, you may not want to delete constraints to do that. You may want to relax them by, say, changing a coefficient or right-hand side or introducing a new activity to the constraint. That will be dictated by the nature of your model and what the IIS means in the context of your model. Let's now move on to multiple constraint deletion. And our first picture here looks really promising. You can remove a group of constraints, and we have two possible outcomes. So if we remove the group of constraints and we're still infeasible, this is great. We remove all these constraints from the candidate set, and we can proceed, and there's still an IIS out there, and life is good. This really speeds up the algorithm. The problem is with the other outcome, where we're either feasible or incomplete, we have nothing to conclude. There's no way to augment the set of known members in the IIS. So this can be illustrated with this next slide. So here's an example where we remove 5 constraints. So we become feasible. But all we know now is that one of these 5 constraints is in the known set K. The problem is we don't know which one. So we have this oval depiction to visualize the process, but our algorithm doesn't see the ovals. It just sees that we became feasible. So the strength of the multi-constraint deletion is in the infeasible case, but it is correspondingly weak in the feasible case. Okay, so given what we just saw, we might ask, well, maybe we can remove multiple constraints by removing single constraints in parallel instead. And this is where our seemingly benign example from a few slides back comes back to annoy us. So what we see here is we're going to take this set of constraints and we're going to, in parallel, remove the x equals 2 constraint and the x equals 3 constraint. So on the individual threads, removing one constraint preserves the infeasibility. And from the perspective of the individual threads, we can discard both constraints. But if we actually discard both constraints, what we see is that that makes us feasible, which contradicts the conclusion that we made by removing these 2 constraints separately, independently, in parallel. So all we can conclude is that one of the K constraints we removed can be filtered out. So we pick one and get rid of it, but we don't know, we can't really take advantage of what we did with the parallel operation there. Okay, so far I've sort of painted a grim picture. Let me finish this part of the presentation with some more positive aspects of how this method works. And one thing is that if you pick a constraint to remove that sits in the intersection of multiple IISs, it basically removes all the IISs that contain that constraint and allows the algorithm to focus on the remaining IISs, which helps it operate more efficiently. And then the other good news that this picture illustrates, and the last slide, is that there is sort of an underlying bias in the algorithm towards finding the smaller IISs that are easier to interpret. So let's take a look now. That sort of ends the section on the background or fundamental operations. Let's now look at how Gurobi 9.1 compares to 9.0. So basically, we have a pretty big test set internally, and overall, across all the models in our test set, including the easy ones, we get a speed up of almost 2x. And if we just restrict ourselves to the last two rows here, the harder ones, we still get a speed up of 5.7x. So I think this illustrates our commitment to improving this computation, even though it isn't an algorithm to solve a particular type of math programming problem, like what we saw in Gu and Toby's presentations. So in terms of where we're at, what we saw here is that challenges remain regarding adding multiple constraints to the known IIS member set at once. And that challenges also remain regarding exploiting parallelism. I didn't talk about it, but another sort of area of challenge, but also opportunity, is making better use of pre-solve and the information in pre-solve that either detects infeasibility or provides information that contributes to the infeasibility. In addition to working on those challenging areas, a few other ideas that currently are under consideration include filtering on the integrality constraints first, so that the subMIPs then solve faster because they have fewer integer variables. This has been successful in some preliminary tests, but it's not clear how to figure out yet when to use it and when to avoid it. And also using Gurobi's fees relax feature can provide additional information in multiple ways that we may be able to better exploit. Okay, so that ends the background section. Now let's move on to a couple examples of using it in practice. And I actually am not going to use it here to just explain an infeasible model, but rather to illustrate that this tool can be used for more than diagnosing infeasible problems. So we'll diagnose an infeasible problem, but in the context of explaining some other aspect of the model phrased as a question about a related infeasible model. And we'll do two examples. The first, which relates to the integrality focus feature that was discussed earlier, is how can I reduce some large big M values in my model? And the second then is which constraints or bounds in the model, which means limits in the associated system being modeled, prevent improvement in the optimal objective value. So regarding the first, let's look at CDMA, which is an open MIPLib 2017 model. Anybody can download it. Gurobi has the best known solution as reported on MIPLib, but proving optimality remains challenging and the MIP gap is still large. So anything that can tighten the formulation could help. The model has a wide spread of coefficients even after doing pre-solve. So let's see what we can do here. And if we look at the pre-solved model, we see some big M style constraints. And besides the trickle flow challenges, which is one problem, these big M values that we see here can create other problems as well. So we have this upper bound of 3 million on this variable ID 36, and we have some logical constraints using binary variables on this ID 36 variable that basically use its large upper bound or big M value, and reducing this value would not only improve the scaling of the model, but it would tighten the formulation and also address some of the issues that we otherwise might need to address by turning on the integrality focus, and then while gaining stability, maybe compromising performance. So if we can reduce the bound on ID 36, we can also reduce the coefficients in these constraints. And to do that, what we do is we create an infeasible model by forcing a relatively large lower bound on this variable ID 36. So I could have started with 3 million, but I was pretty optimistic that 100,000 would be good enough, and sure enough, it was. So changing this from an upper bound of 3 million to this lower bound of 100,000, we get an infeasible model. Now, this immediately deduces an upper bound of 100,000 in any feasible solution. And we could continue doing sort of a binary search like that, but we can do better by just looking at the IIS. So we compute the IIS, and it has 15 fairly dense conservation of flow constraints that look like this, and 5 fairly dense supply or demand constraints that force some notion of flow through this system. This is not necessarily a network, but you don't have to have a network to have some notion of flow through the system. And the other takeaway here is that it really might be difficult to try to interpret this IIS by looking at individual constraints. So let's not do that. Let's instead try to add up the constraints and see what that gets us. And adding up constraints is very easy to do. Here's a code snippet using Gurobi's Python API. As we can see, it's just a very short little chunk of code. And what we get out of this is all sorts of cancellation. And the sum, what we get is one aggregated inequality that includes the variable ID 36 of interest. Because all the variables in this constraint have lower bounds of 0, we deduce an upper bound of 5,000 on ID 36. We therefore can go from the original formulation in the pre-solved model on the left with the 3 million big M values to big M values that are not very big at all, namely 5,000 on the right here. So we've tightened the formulation and we've improved its scaling. So our second example involves identifying constraints and bounds in the model that prevent improvement in the optimal objective value. So I turn to another MIPLide model. This one is solved, but Gurobi really doesn't fare that well on this. It takes almost 9 hours to prove optimality after actually having found the optimal solution in a half hour. So let's get some information about the model by creating an infeasible model where we over-constrain the objective so that this model has no integer feasible solutions. And we can do that by just running the model for a few seconds and looking at the dual bound values that arise early on. So what this is telling us within less than a second is by the time we get to this third line in the node log, we know that there is no integer feasible solution with a value less than or equal to or less than this 603,000 value here in the node log. So arbitrarily, I chose a value of 400,000 because that will ensure that we're using integrality in the infeasibility here, but also by keeping it relatively close to the first dual bound, the submip solve should go reasonably quickly. And again, the resulting IIS is big, but it falls into two classes of constraints. So the first group of 600 has, again, this conservation of flow characteristic, albeit in this case with positive right-hand side values. And then what we see is a collection of fixed charge constraints on some of the variables that appeared in the first group of constraint. So these variables like C1791 here are binaries where they have a fixed charge in the objective. And this is basically the amount of resource. These coefficients are the amount of resource you get if you pay the fixed charge. So once again, we interpret the IIS by not looking at individual constraints, but by looking at groups. And we get a nice aggregated constraint. And what we see then is we can add up the fixed charge constraints and deduce that at least 5 fixed charge binaries have to be paid. And I'm skipping a few details here. You actually have to look a little more carefully at the fixed charges and flow costs. But that too is just another question to pose to the infeasibility finder to understand what's going on. So putting this together, we can take this cut from the previous slide and drop the time from almost 9 hours to 3.1 hours. We can do some refinements on the cut and get it down to 1.2 hours. Or if we're familiar with the way some of Gurobi's cuts work, basically the constraints we looked at in the previous slide are suggesting that aggressive flow path, flow cover, and MIR cuts is probably going to help performance. And doing that just with the original model and dispensing with our sort of less sophisticated MIR cut drops the time to 25 minutes. So what we did here is we were not only able to improve performance by tightening the formulation, but we were able to gain insight regarding good parameter settings. And these two examples are just really scratching the surface of what we can do in this way. A few other questions we could answer include, why does Gurobi reject my MIP start? What does it mean when Gurobi support tells me my model is on the boundary of feasibility and infeasibility? Is a particular constraint or group of constraints in my model redundant? There's many more questions or explanations we can get by posing the question we want in the context of an infeasible model. So to summarize, what we saw is that computing IISs is fundamentally harder for MIPS because we need to solve a series of sub-MIPS. We saw how parallelization has some challenges. We saw how computing IISs is more than just for infeasible models. And partly because of that, we take improving IIS computation time as seriously as we do for our full-blown math programming algorithms. And that was sort of validated with the performance statistics that we showed. And then lastly, to address large IISs, it's important to consider groups of constraints rather than individual ones. Here's a reference to a book if you want to dig deeper. And with that, I'll pass the floor back to everybody else for any final questions about this or previous topics.
Yeah, thanks, Ed, for the presentation. So we have answered a number of questions already online by typing, but there is one question that is still open, which I'd like to ask to Gu. This is not about the IIS topic, but about the previous one where Gu was talking about simplex.
Mm-hmm.
And this is the question that actually I don't quite understand, but maybe you know what to answer. So when training a machine learning model on pivot selection, how many data sets were used and what was the runtime of the training?
So, I mean, we didn't use machine learning for the pivot selection, that's right.
Yeah.
We only use that for decide whether to solve the dual formulation or solve primal formulation and which method to use, primal or dual. I mean, for pivot selection, we could, use machine learning. I mean, we still need to figure out what kind of input we should use to. Yeah. We haven't thought about that yet. That's interesting idea. I mean, to use machine learning for pivot selection.
But we do, I want to add, we do have an dynamic automatic selection for the simplex pricing strategy inside the MIP. And there we use a kind of a multi-arm banded algorithm that tries to learn online the best strategy.
Yeah, I mean, Toby, you, worked on that which algorithm to pick, but we haven't. For LP, pivot selection is more about which variable to enter, and this is like a pricing strategy. And this version for the simplex, we improved that, but not use the machine learning. And depend on some more, the cost, how to update DevX or the steepest norm. Steepest norm is more expensive, and then decide how to switch, but haven't used machine learning yet. So we see one new question. Have you tried to use neural nets to select which formulation or heuristic to use? Not yet. No.
I think I'd like to make a comment about the machine learning questions in general. So, the literature is rapidly expanding regarding using machine learning in different aspects of optimization, particularly heuristics, branching. And I think we can say that all these things are on our radar. And also at the same time, even if we don't use something that officially qualifies as machine learning for a lot of these features, we do have a lot of internal logic already in there to make sensible dynamic decisions based on what we see happening to try to improve performance. But
I would say it's also learning approach. How to branch and a lot of things we are kind of learn, but not using standard machine learning approach. You have specified input, and then you feed the data and let machine learning to get the formula. We just based on some idea, and we think this formula looks good, then just some data coefficient or factor we need to figure out, and then we learn. Yeah.
So pseudo cost for branching is basically linear regression and reinforcement learning.
Yeah.
You can consider it like that. And we have similar things for heuristics. So which heuristics to apply, which to stop applying if they don't work, then great and stuff. Okay, then I think we stop here. So again, thanks for your participation and have a nice day then.